All right, for today, I think there are three things we can do. We can start by going over quickly the solution, maybe not in detail, but maybe just give you some highlights about what you should really pay attention to. The programming part and also the written part, specifically the correctness proof for the Dijkstra algorithm. I still owe you the tracing answer for BFS and also Dijkstra algorithm. I'll get them done either tonight or early tomorrow morning. Okay, I'll release them. But those are the relatively simpler one. So hopefully that one, once I release the result, you can just compare with your answer. And there should be no surprise. On the other hand, the correctness proof of the Dijkstra algorithm will be something you have to pay more attention to. Okay, I can just highlight that a little bit. It's quite a tricky proof to really get right. But do you have to memorize the proof? No, not really. But I think you should really try to go through the proof step. And that one that really draws a very close connection to the algorithm that we kind of went through in the class, also corresponding to the tracing, right? I might just ask you some specific details just about properties for the algorithm. Okay, I'll give you some very quick highlights. Of course, that will be covering the exam. We can still talk about it even after the test. Okay, why don't we talk about just very quickly the programming part, okay? And then just give you some highlights about what you should really pay attention to and how you can practice. And then we can talk about the proof. And then after that, potentially we can take a very, very short break. And then we talk about comparing the graph strategies, about the three different ones. And then to talk about their running time very quickly. I do have some visuals to show to you. So it can also help you prepare for Monday's test. All right, so that'll be the plan. Let's now start with the programming part for assignment number 2. Right? For that one there, you can already download the solution projects from there. So you can assume that you will still be given the edge list graph base package, just like for test number 1. That package will be the same, which will contain the doubly linked node, and also doubly linked list, and also the edge, and also the vertex, right? So this part here will be just the same as test 1. So you will not be allowed to add anything new to this particular package. You got to make sure you kind of get yourself familiar about the basic usage. But if you kind of study through the solution for assignment 1 and 2, you will know that this package here is more than enough for you to really manipulate. All right, so that's something you'll be given. You will be given access to API page as well. So make sure you also get yourself familiar about hash map, hash set, array list, also how you can use generics. Okay, that'll be important. All right, and for the model part, okay, most likely you will be given some partially completed, right? Could be one example, which I said in the guide, right? You'll be given maybe partially completed edge list graph class. And of course, you got to make sure you kind of follow through the implementation strategy for edge list. You have to make sure you declare 2 doubly linked lists of vertices and edges, right? So that'll be the starting point. You want to make sure you always manipulate these 2 attributes. I might just make them public so that I can check their value in the actual test, right? So make sure you know how to manipulate them. Of course, the solution actually walk you through about how you can do it, right? So I want to point out 2 things over here. So number 1 is about the breadth search, which is here. Okay, so I'll just get there first. Breadth search, okay? So you will be given either the fully completed breadth search, which is the solution version, or you might be given the partially completed solution version. But the partially completed, I might just simply take out one of the phases. You got to make sure you're able to complete. So you got to really go through how this should be really implemented and try to practice that yourself as well. I think the solution version goes very closely with how we trace the code. So that should be no surprise, right? So let's say you're given some breadth search, okay? And then you're going to take that one to answer some graph question. The one that we did, for example, about get number of connected components is a very good example there, right? So basically, you're going to get a return value from the breadth search, right? So if you, for example, if I move my mouse over the breadth search, bear with me, right here, right? You can see that the breadth search is actually used right here, right? It's basically being used just to return what are the edges being marked throughout the traversal. From there, we can actually try to get some answer for the graph question, right? Just about number of connected component is definitely one example. So you may just want to maybe go over maybe what we talk about as an example graph question you can answer and think about how you can use a breadth search to implement that, right? So I might just give you one of them or something similar, okay? So that's what you can expect on the programming part. Of course, you got to make sure you know how to use the collections, hash map, hash set, array list, and also generics, that's for sure. Okay. Any questions about the programming part? Yeah.
Can I use Q for first search?
Yes, you may. If that's one of the Java API, no problem, you can use it. Yeah, but I just personally prefer just using array list because I can always treating the front side, the first element as the front. You can do that as well. Yes, yeah. Any class that's part of the Java API library, you can use it, no problem. Of course, if you wanted to use primitive array, I wouldn't stop you from doing that too, right? You can use anything basically. Okay, it's completely up to you. So think about how you might actually implement similar question. All right. Any questions about programming part? So you wouldn't be so wise to really spend time going over detail. You might just easily get lost in the implementation detail. So think about how you might return the mark edges from the Bradford search, and then how you can go from there to answer the graph question. So that's most likely the question you will be given to implement. Okay, and of course, make sure you know how to import, export, submit, things that you did already, right? Josh, you okay? Good, awesome. I want to be sure. Okay. Okay, that's about the programming part. Right? Again, in the test, I really have no preference, suggestion about whether you should really do the programming part first or the written part. It's really up to you, right? So there will be something you gotta type, something like a multiple choice. You can completely decide the order you want. Okay. Anyway, that's about programming part. Okay. Awesome. Okay. And then let's now talk about the written part very quickly. Okay, I just actually updated the PDF about a few minutes before I arrived because the fire alarm actually stopped me from going back to my office. So I had to do some last minute changes right before I came. You can download the PDF, but as I said, let me take a look with you. Okay. So this is the latest version. For now, you can see that I still got the solution for Bradford search here, outstanding. And also the Dijkstra tracing, also outstanding. I'll make sure I put them up, right? You can definitely compare your answer. So assuming that I have done that, that should be very straightforward to do, right? Just according to how we did it in the class, right? I'll make them available to you. All right, so now about the correctness proof, right? I try to maybe stay a little bit higher level to really give you some highlights, some big picture about what the proof is really trying to kind of go through logically, right? There will be some details you will actually have to follow by yourself. But I think that this correctness proof over here ties, it goes very tight together with the algorithm, like a pseudocode that we spoke about when we talk about the running time for Dijkstra. So make sure you also understand the algorithm very well about individual step, all right? All right, so here, right? So we're gonna do by mathematical induction. Okay, let's just highlight the part you really want to pay attention to. So we actually want to do by induction. Specifically, we want to do an induction on the size of this imaginary set. Right? We talk about capital S when we trace the Dijkstra in class as well. So when S is simply equal to 0, that means we haven't gone through any iteration just yet, right? So that'll be the base case, as we'll see. And then we assume okay, so you can think about, let me just go through the very quick, you'll see the different phases. Okay, phase number 1, base case. So when the cardinality or size of S is simply 0, no iteration has gone through just yet. So that one should be rather trivial to really argue about. The inductive hypothesis will be satisfied. And also, this one here is about the looping variance for Dijkstra that we spoke about also in class, right? I just put it in a formal way, right? We also talk about this formal notation in class as well. So phase number 1 is about base case. Phase number 2 is we assume some property about when the size of S is exactly equal to K. K here means we have already iterated K times of the body of the loop, all right? So that means K iterations have done already. Meaning that every time at the end of each iteration, we want to remove one vertex from the priority queue and put that particular vertex into this capital S set, right? So that means the capital S set is going to keep growing one by one, okay? So this will be the inductive hypothesis that you're going to see. So this will be the inductive hypothesis, and the final phase, which will be the inductive step. So that one there is going to somehow argue about when S has grown to k plus 1. And the plus 1 over here is the new node, which we call U. Okay? You will see that in the proof. So this is a new node that we are trying to process in the new iteration. We want to say that assuming that all the previous k iterations actually hold the invariance, we want to be sure within one extra iteration, this can still hold the property. Right? That's kind of an induction we're doing. So this correctness proof is very interesting. We are mapping very closely about each step to exactly the phases for the iterative algorithm. Before the iteration, S init, and also after a certain number of iterations, K, and then the final iteration to really show that it will hold in general. All right, so that's a general structure. Okay. And then, all right, so you can take a look at the base case, right, before the iteration, and also inductive hypothesis, right, the notation here, and then the inductive step, right, over here. Okay. So that one really will take some time for you to really stay isolated, just to study through the detail. I try to be as thorough as possible, also adding lots of explanation and details over there. But you can definitely give me some feedback at some point. Just tell me which part can be explained better. But I hope at least it's a very good point for you to, at least for you to also figure out certain gap by yourself as well. So I just want to point out over here. Okay. So you can see here for the inductive hypothesis, we got a conjunction. We call this is a left conjunct. And this one here is called a right-hand side conjunct. Right? We're going to prove them separately. Okay? So what you will see is this part here is going to argue about the right conjunct. Okay? We kind of argue about this one first because that one's a little bit easier to argue about. Okay? We'll do that one first. Okay? And then you can actually take a look. This one here is mapped very closely about how you're going to change the capital D value for one of the adjacent vertices. Okay, you will see that. Right? This one should be quite easy to understand. The next page is just about how we can argue about the left conjunct, meaning that once you have put a particular vertex into SK, the capital S, right, the finalized set, in that case, the capital D value should be exactly equal to the true shortest path. All right, the distance of the shortest path. So now if you look at that, so that one would be actually, yeah, the blue one. Okay, so this will be the right conjunct. Left conjunct, beg your pardon. Okay, so this will be the left conjunct that we are proving. All right, and we're going to split that into two cases for completeness. But case number one is trivial, right? But when you look at case number two, okay, now here's the pattern for case number two. Okay, you will see that I started the proof by saying explicitly we prove this case by contradiction. So you have to kind of recall what proof by contradiction really means. I'm pretty sure you learned about it maybe from 1019, 1090, the previous course. Okay, proof by contradiction goes like this, which you will see the pattern. Number one, we assume something. Okay, and then all the arguments subsequent to this is going to be consistent with this particular assumption, right? However, by following through this assumption here, by arguing point number one, point number two, and also point number three, okay, you can see all these 3 points are really structured around that particular assumption. However, by doing that, we actually run into something that contradicts with the assumption, in which case the assumption originally cannot be true, right? So that's really the essence or spirits for proof by contradiction. You can see a final sentence here say it contradicts with this particular assumption. So that means the negation of the assumption must be true. Okay. So this will mean the negation of the assumption must be the case. Should be the case. Okay. So after this, we will be able to show that because this is not the case, it turns out the negation of that, which means D of U equals DSU, is actually something that we want to prove eventually. All right? So, of course, to really see how we can actually construct stuff around the assumption to really create a contradiction, the setup is actually quite long. So you're going to go through 1, 2, and 3. Okay? And then, okay, that'll be the proof. About 2 pages. Okay. Of course, I try to just adding lots of details inside the proof itself, just for you to kind of see how we can build up the actual logical reasoning. But you want to pay more attention to the insights about the connection between the mathematical property and the actual algorithm steps. So that's something I will assume you will know pretty well before the test. Okay. Questions in general? Sarah, go ahead.
So the negation of the current assumption would
Yeah.
be less than equal to rather than just equal to?
It's a very good point, okay? In some way, I kind of leave a gap over there. That's a very good point. I can also talk about it. It's a very good point. So you can see that, so if you look at this assumption here, so if this assumption is actually wrong because we run into contradiction, right? So that means the negation of that, which would be capital D of U, should be less, let me write it down. So in other case, larger than SU. So that'd be equivalent to, if you do some simplification, so D of U less than or equal to D of SU. Okay, so now this less than part is not possible because if this guy here happened to be less than that, then the fact that this is the true shortest one is not the case. We kind of put that the assumption. Okay, this is impossible. Possible. Given that the D of SU is the true shortest distance. Since we assume that is already the true shortest distance, it's not possible to have something even smaller. Not possible. So it got to be equal to. So I could have put this like a less than as well in the proof at some point, Yeah, but it's good. It's good that you brought it up. Okay. Okay, very good. All right, so if you haven't got a chance to go over the proof, maybe spend some time, especially try to study that together with tracing, the pseudocode, running time, right? Just to make sure you understand the algorithm for Dijkstra very well. There's definitely going to be something you have to know for the test and for the exam. All right, good. If no further questions, why don't we do a little bit of the running time for graph algorithm? Okay, we'll see how long it's going to take. May not be long. Okay, so the other day in the class, we kind of introduced also about the adjacency matrix over here, right? So now we can compare all the 3 together. Let's do a little bit of summary about how we can understand about the 3 strategies. So this one here is the edge list, the green one. Okay, this one is the edge list. So we basically got a list of vertices. We got a list of edges. For each, beg your pardon. My apologies. Right here. Okay, the edge list is right here. Okay, the blue one. Okay, gotta be careful. So we got the linked list of vertices. We also got a linked list of edges. For each vertex, you also have a pointer back to its position in the vertex list. And also for each edge, you also got a pointer back to its position in the doubly linked list, right? That's what we learned from test number 1. So this will be the basis for the other 2, right? This one here is called the adjacency list strategy. Adjacency list, okay? So the main thing that we have introduced in this one here is called adjacency edges, okay? So this is the adjacency list strategy, okay? So for this one here, you still got a list of vertices, you still got a list of edges, and also for each individual vertex over here, you still got a position pointing back. That one's the same. And also for each edge, you also got the position pointing back. So that part is just the same as edge list, but we do have something new, okay? What's really new is for every vertex, for example here, we also have a reference to another list. It's the incident edges list. All right, so that's the new stuff you want to know. That one there arguably is going to save some running time as we go for some operation. So this will be incident edges list that we have. All right, so that's really the thing you want to highlight. Okay. And then the final one here that we introduced just on Wednesday is called adjacency matrix. Adjacency matrix. Okay. So this one here, think about it's almost like edge list, almost like it, because you still got vertices, you also got edges, right, over here, except we have another attributes for the graph class. Okay, so the attributes is right here, matrix. Okay, called matrix. It can be done in a 2D array, or it could be an array list of array list. Okay, it's kind of up to your implementation strategy, right? Let's say it's a 2D array, right? So the matrix here is going to store edges. Okay, so for example, let's say here, and also every vertex is also going to have their index. And the index here, for example, 0, 1, and 2, they simply correspond to how many rows you have in the 2D array. All right, so for example, let's say for this particular vertex, right, it has the index 1. So I can go to row number 1. That way, I can actually see I got one edge right here. So this is the edge that has to do with vertex A. More like an incident edges, one of them. Okay. So that's why we said the other day, if you follow through this index for the vertex over here, you can see that this is the row that represents the incident edges of vertex A. All right. I don't really have that original graph, over here. I don't have space, but I can definitely check back to the slides to see what this one here really represents. Okay. Also, when the graph is actually undirected, the edge will be like symmetric. For example, you can see that we got, so you can see that over here, matrix. So let's say, for example, I got 1, 0. 1, 0 will be the same edge as matrix 0 and then 1. All right. So you can 0 and then 1, which is here. So you can think about this edge and also this edge here. They point to the same edge objects. For the undirected graph, you want to have that symmetry. All right. For directed graph, you don't need to have symmetry. Okay. That's something you can also pay attention to when you see the visualization. Okay. So these two are the same. Okay. Any questions so far? Yes.
When we implement it, do we use the same object for the symmetric case?
You'll use the same object exactly. Yeah, that you're supposed to.
It's not just like a clone object.
Actually, you don't really want to use clone object because in that, conceptually it's not even right. Because let's say, for example, if I got, let's say, A here and B here, right? I want to represent this particular edge. If you look at the graph here, it's just one edge. But if you try to make a clone, you're talking about there's another edge over here. Or there's a double edges, for A and B, which doesn't make sense, right? So the same objects. Yes. Okay. All right, that's good. All right, so let's now try to just go over, I think we have time, so why don't we do that thoroughly since you guys are here. Okay, that'll be to your benefits. Why don't we just go over, there's a table there on the slides, I can show you quickly. And then I'll go over all the entries with you, okay, so just to justify the running time. I think many of them are very straightforward, only a few. I will also write down the steps that you have to think about. Of course, you got to verify a little bit more, by yourself when you study for that. So if you go to the slides over here, okay, right here. So in the very last one, okay, so we're going to go over this table here, right? So there are many cases we're going to consider. Okay, let's go over all of them. Okay, I think we just have time. Okay, why don't we go over just maybe 1 or 2, 2 or 3, and then we'll take a short break and we'll go through the rest. Okay, let's do that. Okay, the first one. And the starter page is actually the one I kind of posted for the lecture on Wednesday. You can also take a look. It's the starter page is also there. Okay, the first one. Okay. Let's now take a look to see what should be the running time for this, okay? Let me peek on my notes so I don't make any mistake, all right? Right here. All right, the first one here is rather simple, okay? So this one here is just about how many vertices do we have in the graph and how many edges do we have in the graph, right? That one there, for example, here, number of vertices should be 1, 2, 3, 4. Number of edges should be, for example, here should be 1, 2, 3, 4. Or in this case, it would be 1 and 2, right? So since we're using a doubly linked list to store the vertices and edges, there is one method which will just return the size of the list. That one's big of 1. Okay, that one's simple. Okay, so this one here, we don't need to say too much. Big O of 1 for all of them. Big O of 1 and also big O of 1. Okay, I can simply say all of these, both of these can just be implemented by returning the attributes of doubly linked list, right? Of course, if you don't have that size attribute in the doubly linked list, you just want to calculate the size from scratch every time, it will be a different running time. We're assuming that you got attributes, okay? So for example, size, okay? Right, it's a very efficient operation. Okay, let's see the next one, okay? And this one here is about, I want to return, if you recall your assignment number 1, the iterable of vertex and also the iterable of edges. Dynamically can just be an array list of vertices and also array list of edges, right? That's what we did in the assignments, okay? So now what will be the running time, right? You can think about, for example, here, I got a doubly linked list of 1, 2, 3, and 4 vertices. How can I return an array list of 4 vertices? Well, you basically just go over one by one, and then each one of them you're looking at, just add them to the array list, and then return, right? So now, any idea? Josh, running time. Big over n. Okay, for vertices. How about for edges?
M or some other letter.
Yeah, exactly. Very good. Yeah, exactly. Straightforward, right? Yeah, if that's not straightforward, I can still ask you, so just to see how you might think. Okay, big O of n. We always assume number of vertices should be n, number of edges should be m. Okay, and also the step you want to watch out for is you want to go over the doubly linked lists to create the iterable objects, right, for these two methods. For example, basically in Java, any collection is an iterable. It can be an array list, or it can be a set, or it can be something else, right? Or queue, for example. Array list. All right, so that's the second one. Okay, it's going to be big of n for all the 3, big of n for all the 3 as well. Okay, the same. Right. Okay. We're about halfway in the time. Okay, I also, why don't we take a very short break? I will just organize something and then we'll resume. Just 2 or 3 minutes, okay? Okay, so now let's talk about how we can get an edge, okay? So we're basically given 2 vertices, assuming that these 2 vertices are in the graph, okay? What's gonna be the running time for each one of them, all right? Let's start with this, edge list. That's something we did in assignment number 1. So basically, you can see that this is kind of like an origin, like a destination, but doesn't matter. You just got 2 vertices over here, right? To really find out whether there's such an edge, because for each edge, you actually got origin and also destination. So these are the 2 attributes. But you're not too sure which one is going to fit. So you just have to go over all the edges one by one. Hopefully, you will run into one where origin is U, destination is V, or the other way, right? That's basically what you're going to find out. All right? So it sounds like you're going to go over all the edges. So this one here, you're going to go over this particular list right here. Okay? Basically, you got to go over all of them. So you have to go over all the M edges. And for each one of them, you have to check against the origin and destination. Oh, you know what? Let me phrase it a little bit better. Okay, you gotta check for the origin and destination. You gotta check for the origin and destination against what you're given. For example, U and also V, right? If you got U and V, you gotta check the origin and destination for each one of them to find them out. If you can find a match, so that means the edge exists, and then return that edge object. If it doesn't exist, then they are not connected, you just return null. All right, so definitely the worst case running time will be number of m edges to go through. All right, that's good. Let's now talk about over here incident adjacency list. And the incident edges attribute that we added to this graph here can really drastically improve this particular scenario. All right, so let's say, for example, let's say we want to go over, let's say we want to say the edge between, let's say A and B, for example. Let's say get edge between A and B. And in this case, of course, both vertices exist. So we got A here, and we got B here. Simply go to those two vertices first. And then what's really unique about this strategy here is each vertex has their incident edges list. Okay? So we can simply go to the incident edges list for A, which is over here. And also incident edges list for B, which is over here. Right? And then from there, we actually want to see for either one of them, are we able to find the edge whose origin and destination are exactly A and B? Right? It's a little bit like a back to the edge list kind of idea. So either, for example, we can just go over this edge over here to see if the origin and destination are A and B. Oh, sorry, let me say it again. You can go over, for example, this edge over here, in which case the origin destination, well, just happen to be A and B, so you know that this edge is good, right? And, or you can just go over another edge to see if the origin and destination, if they're not exactly A and B, you know it's not an edge, right, etc. So in the worst case, you have to somehow exhaust the incident edges list for the vertex. So now the question is, which one should you exhaust? Running time-wise, to be efficient. Should I really choose A here or B here? What doesn't really matter? B here? Because? Yeah, it's smaller, right? Because you never know like what the degree might be for a particular vertex. There's no connection about which one might be larger or smaller. Choose a smaller one. All right, so that's the key, right? So this one here really talks about this essence about why adjacency list can be efficient. All right, so it turns out the running time. Let me just go over, just tell you what you should do. So you should really choose the minimum degree among the two, okay? So you can think about for A here, we know that the degree of A is 2 because we've got 2 edges. And the degree of B corresponds to the size of this list, which is 1. Okay, and 1 here is the minimum. Okay, so we choose that. Okay, once you choose that incident edges list, you do something very similar to the edge list case. So you're going to go over the smaller incident edges list and check the origin and destination against, in this case, of course, A and B. Okay, go to the smaller one. So now, how do we express the running time? Josh.
Isn't this still O of n depending on the graph structure?
It could be. Yeah, I agree with you in some way, yes. But I would say try to, again, similar issue as I kind of mentioned to your fellow student. You're talking about something that depends on the graph structure, in which case you might have up to maybe n-1, edges to all the other vertices. Yes, I agree. But let's talk about the most accurate bound without worrying about how many edges you might be connected to, okay? So it seems that we are basically choosing between either the degree of A or the degree of B, whichever that's smaller, okay? So the way we're gonna express the running time goes like this. Is it gonna be a big O of the minimum of either the degree of U or the degree of V. So D here is just the degree. Choose a minimum. Okay? Of course, in this case, minimum is possible. N minus 1, right? When the graph is completely complete. Right? It's possible. But I think this is more accurate. It's definitely more accurate to say that, because you don't necessarily always get to the complete graph. All right? Okay, we figure out two of them. Okay, one here and also one here. Okay, what about the adjacency matrix over here? Okay, we still somehow have to go over edges, but now are we able to improve anything? Yeah, Josh, go ahead.
If the graph is acyclic, is it?
It means it's undirected. Is that what you want to say? So here, actually, having a cycle or not doesn't really matter, because we want to find just at the edge between two vertices. So,
More like in the, when we're representing a graph structure, if you have an acyclic graph, then the adjacency, like the biggest adjacency could be is 2, because you have like point here.
I don't think we should really consider if there's a cycle. You're talking about having a cycle, right? Is that what you're talking about? Right. Having a cycle or not is not going to impact the running time here, actually.
Because I'm imagining if we have a graph with no cycle, then at most each edge can have 2 adjacent. At most each vertex can have 2 adjacent edges. So like the largest value.
Not necessarily. Because, for example, you might still have, well, for example, you have an arbitrary number of vertices. Let's say you still may have a complete graph, for example, here. You still have a cycle, right? So the number for, I'm saying the degree, yeah, it's the complete orthogonal concerns, really, like having a cycle or not, or incident edges. They're a completely different concept. They're independent. Okay, good. So now, any idea? For example, if I want to get, if there's an edge between A and C, for example, how do I get it? One moment. For example, if I say get edge. So think about this one here. If I say get edge, A and C, how do I get that edge objects? Do I really need a loop? Sarah, go ahead.
Index value from each.
From each? Okay, so index for A will be 1. Index for C will be 2. So 1 and 2. What should I do once I get 1 and 2?
Then you just plug them into the matrix and see if there's a edge value.
Yeah, to see if that's null. Yeah, exactly. Yeah, that's exactly right. Good. Maybe that's what Josh is thinking too. Okay, completely right. All right. So this can just be boiled down into, I can go to the matrix, right? And then I'm going to specify 2 values over here, right? I'm just running out of space. So value 1 and value 2. Okay. So value 1 would just be, for example, I can go to A dot get index value. You will see that one of the methods in the graph is actually this method, accessor, to get an index. In this case, it's going to give you 1. And the second value here is going to be C dot get index. Okay, that one there is going to give you 2. All right. Okay, awesome. Okay. Yeah, I think just for the very first or 2, we can go very thoroughly, very slowly. So once you get an idea about how to manipulate these 2, others will be also straightforward to actually figure out. Okay, let's do one more. Similar. Let's say we want to get, so all these 4 have the same running time. They will work slightly differently, but very similarly. Okay, so I will just talk about one of them. The other ones you can do as exercise to see what the different details might be. Okay, so why don't we do out edges? Okay, so assuming that we have a directed graph. We want to find out, given a vertex V, okay, I'll write it down. So let's say we have some vertex V. So there might be some incoming edges. There might also be some outgoing edges. So we want to figure out all the outgoing edges right here, right? That's what we want to find out. So of course, you want to find out all those edges where V is the origin, right? That's obvious, okay? So that's the main insight. So all these out edges where V is the vertex. Where V is the vertex, is the origin vertex. Origin vertex. All right, so let's now figure this out, right? The other three, you can now take as exercise to figure out. All right, the first one. Edge list. Edge list in some way is kind of straightforward. Anytime you want to somehow search through edges, you don't have many options. You don't have incident edges, right? So all you can do is you still got to go through this, right? You want to go through this one by one and find out all the edges where the V you're looking for is the origin. Agree? Okay? Running time, big over M. All right? Should not be tricky. Okay? You still want to go over right here. Okay? So go over the M edges. You want to count those whose origin is U. Okay? Is V. Beg your pardon, V. Okay. All right, good. And what about this one here? Almost the same, except we now can do very focused search. Rather than searching all the edges, we can only search those edges that's already known to be connected to V, which will be incident edges for V, right? So let's say we want to get out edges for A, for example. In that case, we'll just have to, first of all, target A, which will be presumably the arguments that we pass, right? And then go to its incident edges. So we know maximum 2, we got to go over. 2 is exactly the degree of that particular vertex, which is the argument, right? And then we simply go over this list in the same way. Find out all those where A is the origin. You'll find out the only one that's the origin is this one here. Okay, just one edge. Okay. So this is the origin. All right, very similar. I'll write it down. Okay. So you want to go over these, which is arguments, incident edges list. And you want to count, so this part is the same. Count those whose origin is V. All right, awesome. Running time, big over N or much smaller? Smaller? How do you express that smaller number? Big O of?
The degree of whatever vertices.
Yeah, good. Since we'll talk about V here, right? Big O of the degree of V. Good? Pretty close. Good. All right. What about our edges for V, given we got adjacency matrix over here? All right. What should we do for this one here? Apparently, it's very similar, right? Because here you want to get the incident edges. Incident edges of A, for example, will just be the row with index 1, which is the index for vertex A. Question?
More like, isn't this more similar to the first one? Because like
Maybe more similar to the second one.
because the size of our array, like the length of each row is going to be based off the number of vertices.
That's true. That's true. However, you can do more efficiently in the following sense. You can see when you say the first one, you meant this one here, right? Yeah. Okay. So this one here, the way to do it is by going over all the edges. That's what we have, right? But I think it would be better, in which case, just go over this edges list, right? But that's not the way to go because it will be big of n. We can do better.
I thought not over that, we would go over like a row in our array, but the length of the row in our array.
Yeah.
I thought that corresponded to the number of vertices we have.
Yes, exactly. So you think that'll be the running time?
Well, that one was okay.
That's okay. Let's give it a try. Okay, first of all, we know that this part here is more or less the incident edges. Not exactly, but more or less the incident edges for V. So let's say this. For this one here, so we get, let's say, our edges of A. Our edges of A. So first of all, we start with the A itself, right here. Okay, and then we see that that one has the index 1. Get its index, so we know that all the edges that has to do with A must be in this particular row. Some of them might just be null, in which case they are not counted as incident edges, right? So you basically go over them. Okay, Josh, how many columns do we need to go over? Yes, exactly, big over n, right? So you basically have to go over every column in this particular row. And then for each one of them, you go to the edge if it's not null and check the origin. Okay, I'll write it down. Good. I think so far the example we have seen, they just already kind of really exploit, about all the unique features about different strategies over here. All right. And of course, when you I'll write it down. Give me one moment. And when you, for example, get to this particular edge right there, you can see the origin happen to be just A. So that'll be the edge to return. Okay, let's write it down. So briefly speaking, what you have to do is you have to, okay, so I'll put it here. You have to go over the columns at the row index by, okay, for example, V, right? By V, or in this case, A as well, okay? And then you want to count those, again, whose origin is V. Of course, you gotta double check it is not null, right? This is not incident edge. It's basically just null. All right here. Okay, question so far? We're more than halfway, okay? Okay, I would suggest we do, we can just do maybe one or two more, okay? The next one there is about how we can insert a new vertex. Okay, let's say we want to introduce a new vertex. Okay, this one here should be quite easy. Josh, any idea, please? If you want to insert a new vertex, let's say for this one here, presumably a new vertex has no edges connected to it, right? So what? What'll be the running time? How come?
Because we have we can just put it, or we can just add one more
to the doubly linked list, right? So doubly linked, so let's say insert last is going to be big of 1. Yeah, exactly. Very good. Okay. Yeah, so basically big of 1. So you can think about these two, actually for both of them, okay? It's going to be big of 1. You can simply insert last to the doubly linked list of vertices. And if you want to insert edges, it would be something similar, but not exactly similar. Okay. Now, let's talk about the nightmare for adjacency matrix. All right, so for here, if I want to add a new vertex, so let's say, for example, right now I got A, B, and C, right? I want to introduce D, let's say another vertex over here, right? Of course, let's say vertex here. But what else do I need to do? It's not enough just to have a new vertex here. I may have to modify the matrix over here, right? Because potentially the vertex D might connect to other vertices at some point. I want to get prepared for that. Any idea? Go ahead. Big of n? Why n?
Because that's the number of vertices that you have to increase the matrix with.
Okay, let's go carefully with that. Okay, so it sounds to me you want to grow the matrix. Am I right? Okay. So, oh yeah, go ahead. I heard n squared as well. Okay, let's go with the Sarah first, right? So maybe you haven't thought deeply enough just yet. If you actually want to add a new vertex, you basically want to grow the matrix. So we used to get 3 by 3. So now, since there's going to be a new index, for example, 3 here, and also 3 here. So that means it's going to be basically 4 by 4, like that, right, conceptually. So now how do we create that 4 by 4? Of course, you can create that 4 by 4 2D array objects, but what else? You have to go over to copy the existing smaller matrix to the larger matrix. That one is going to cost you n squared.
More question. Couldn't we, instead of doing a doubling strategy, couldn't we do a quadrupling strategy? So that the average case ends up being O of n rather than O of n squared?
Oh, you're talking about dynamic array, right?
Where like each time we reach the limit, we add in.
It's interesting idea. You're basically saying every time you,
Like, I don't know what the math would work out, but in my head, it's like roughly the same.
it's interesting. Let me think about it. I know exactly what your intuition is. So what Josh is now saying, even though it's 2D array, but think about it's more like a collection. So if you think about dynamic array like a doubling strategy, so now we're going to say every time rather than just creating exactly the dimension for a number of vertices, you can say, okay, let's say now we want to add a new vertex, but we'll grow the matrix like a double. Rather than 3 by 3 to 4 by 4, it's just a 3 by 3 to 6 by 6. I'm not too sure, actually. It's interesting, yeah. That could be something to think more deeply about math, okay? Anyway, for this one here, it turns out n squared is really what you're suggesting. Okay, let's now write it down, okay? Basically, what we're doing here is we're going to go from n to m by n to n plus 1 to n plus 1 matrix. However, the costly part is once I create, for example, this 1, 2, 3, 4, 1, 2, 3, 4, this larger matrix, I have to copy everything from here into the new matrix before I can assign the matrix reference to here. So that one there is going to be I'm going to use a nested loop, double loop, right? But it's going to be big O of n squared to do copying.
Can that make the matrix be the array list of an array list so that you don't have to worry about copying the elements over to increase the size?
Potentially you can, I think. But since we are assuming that it's a 2D array.
It's 2D array.
Yeah, it's a good question. Okay. I'll put as a side. For 2D array for sure, because you can fix size, right? But if you use array list, what if array list of edge is used? Okay, I'll put it here as a question. Okay. All right, good. All right, let's now see, just got 2 more. Okay. What about we want to remove a vertex? All right. If you want to remove a vertex, what should we do? All right. So let's say, for example, if I remove, if I simply got, just say, I'm going to draw here. If I got, for example, let's say without a label. Let's say here and here. What does it really mean when I want to remove this particular vertex? I do not just remove this particular vertex just from the list over here. I got to remove all its incident edges as well at the same time. That's what I should do, right? That's a complexity we have to deal with, all right? So now What about for edge list? What should we do to remove not only the vertex, but all its associated edges? What should we do? Go through the list of edges or go through the list of vertices?
Go through the list of vertices to remove the vertex, and then go through the list of edges to remove anything that has the vertices after it.
Except for the first part, you don't really have to go over all the vertices. You don't have to, because you pretty much know the V already. Okay, I'll just go over that. Okay, so first of all, you have to go over the edges first. Go over all the edges right here. Okay, go over them. And then you're going to find out all the edges where the origin or destination is the vertex you want to remove. All right, so for example, you can see that this one here actually points back to, let's say we want to remove vertex A. Okay, I'll just put it down. If you want to remove vertex A, for example, right? In that case, anything that's going to point back to A as origin or destination should be removed. For example, you can see this one here and also this one here. So these two edges ought to be removed. They need to be. All right? So let's now do that. So now what we do is you want to go over the N edges and remove those whose origin or destination is the vertex V. Okay? So now, one thing that's very important, right? How do you remove them efficiently? For example, if I want to remove, let's say, this particular edge, how do I remove it from this list without having to go over the list? What should I do? Josh, any idea? Okay, it's okay. So now here's a question. So let's say I want to remove this edge. Is it possible to remove this edge without having to go over this list of edges? Is it possible? Is it there more efficient way? If I simply just go over this list of edges to remove anything that's equal to this, it's going to be big of n, right? Is it possible to do it a little bit better? Sarah, any idea?
I was guessing how each edge has the pointer back to its edge.
Aha, that's exactly right. Because, for example, you can see this one is pointing back to the position, right? For that one there, you might just say E dot, you can say something like, you can say E dot remove. And then you can say O dot, for example, get position. Okay? That one there is going to give you constant time. However, because after all, you still want to go over this edge like a list of edges to see which ones will get the origin for the vertex. So you still boil it down into big of n. Still. All right? Yeah, so just like a sketching the idea, but overall it's going to be big of n. So you should really try to write down the detailed step to see how this can be done. Okay? Okay, so that's big O of n right here. All right, let's do two more, and then I think the final one is very similar. I can leave that to you. Okay, very simple. Okay. What about I want to remove a particular vertex, but for adjacency list? Should be very similar, right? Josh, any idea? Huh? You're still processing the previous one, yeah. Similar, actually. Sarah, any suggestion? Go ahead. Okay, let's say we want to remove the vertex A, for example. Okay, let's say that's what we want to do. So let's say we want to remove A right here. You're quite right. We do have its incident edges. So let's say we want to remove A. The incident edges is exactly here. But once we find out the incident edges, what should we do?
Get the
Okay, so here the more complexity is, right? So now you can see that the edge objects, right? You can think about the edge object right here. The edge objects is being saved in two lists. One is the global edge list. The other one is the incident edge list for individual vertices. You want to make sure to remove from both kinds of lists. All right? So that means, for example, if I want to remove, let's say, this particular edge, for example, what should I do? I should first of all remove itself from E using this position. I should also follow its, I should also go back to this position here, which will give us the incident edge list for B. I should also follow this position here to go to incident edge for A as well and remove them. So, but of course, all the removal is going to be big of 1, but you ought to know exactly which ones you should really go to. I'll write it down. Okay, so here you basically have to go over these incident edges lists and remove all edges from there. However, I'll put a star here. There's some detail, subtle detail you have to know. Okay, I'll put a star. The star, I'll put it here. Each edge should be removed from 3 places. Number 1, it should be removed from the global edge list of edges. The list of edges by using the position. Number 2, it should be removed from its origins vertex incident edges list. Okay? Its origins incident edges list. And also number 3 is destinations incident edges list. So these are the 3 lists. They should be removed. Of course, each one of them is going to be big of 1, but you ought to know exactly which 3 should be removed. All right? That's good. Now, final one. What should we do to remove vertex from here? Yeah.
It was all of the
Oh, yeah, sorry. All of what? Sorry, I forgot to mention. Yeah. How do you think?
I think it's still all of the degree.
Yeah, that's pretty much true because once you go to the incident edge list for A, for example, this size will be the degree of A. But for each one of them, when you want to remove them, each edge should be removed from 3 places, but each one of them is going to be big of 1, right? So, okay. So it's going to be big O of the degree. Very good. Big O of the degree of V. Okay, awesome. Yeah. Okay, final one. How do we remove, for example, let's say vertex A from the graph? What should we do? Yeah, what should we do here? Apparently, well, there are, of course, one way that can be very complicated is, let's say I don't want to shrink the matrix from maybe 3 by 3 to 2 by 2. Let's say I don't want to do that. In that case, it's going to be tricky because you might want to say, now I want to abandon the index 1 for A. I might just set everything here to be null. Everything here to be null. So I'm going to keep track of about index 1. Maybe that's going to be for the next vertex to be inserted. That might be a way to go. But it might just make things too complicated, right? We can go for the simple way. Let's say the way we're going to do that is we want to shrink maybe the matrix size. Yeah, go ahead.
Do we even have to set everything to null? Like, can we just forget that, like right now we have that
Yeah.
A corresponds to 1, but if we just forget that, then we don't have to, like we can still have the values in our array, but then not bother updating.
No, we're going to remove it conceptually, actually, because if you really decide to really remove this A here completely from the graph, you have to make sure all the associated, all the incident edges to that particular vertex are removed as well. right? So not only that, I can tell you that not only that you got to set maybe the index 1 over here to null, but also these edges ought to be removed from the edge list as well, right? So those you have to do, right? All right, so for this one here, I'm going to write down very briefly, but you can think about what you may want to do. It's going to be dominated by like this, okay? So basically, for this vertex here, you have to completely conceptually wipe out this column and this row. That's to do with index 1. Okay, index 1. Okay, so we are shrinking it from n to n into n minus 1, n minus 1. But we still want to do copy, right? The old contents. So this one here, you want to go from n times n to, just 1 minute, and then we're good. Okay. Shrink it down to n minus 1 times n minus 1. But you want to copy over the contents, right? It's still going to be big over n squared, which is, well, the copying. Right, so that's what you will see. It's also expensive operation. Yeah. All right, the final page is for you to do exercise, right? Well, I think we covered just enough all the operation for all the graph. I think these three will be quite easy for you to try. All right. Questions? All right. So everything has been covered. Basically, well, this is just like an exercise from what we covered on Wednesday. So yeah. So for test 2, take a look at the graph, and then I'm going to update definitely the solution to the 2 BFS and also Dijkstra over the weekend. You can double check your answer as well, and then I'll see you on Monday. Williams Small Center, right, for the test. Awesome. Okay, I'll see you later.